Hello everyone. Today we will be looking at the Chefina and ranges problem from the December 2019 long challenge. As we can see, the problem had only 552 successful submissions in Div 2 and 563 successful submissions in Div 1. I will show you how to solve this problem easily. For any problem that I come across, I like to follow what I call as the 10 commandments of code. They go as follows. Thou shalt first read the problem. Thou shalt try to understand the problem. Thou shalt search for the simplest algorithm. Thou shalt locate the best algorithm. Thou shalt dry run the algorithm. Thou shalt find the best data structures. Thou shalt code the algorithm. Thou shalt optimize the code. Thou shalt test the code. And thou shalt break your head debugging the code. So let's move on to the first commandment, reading the problem. A common mistake that people make is that they try to understand the problem on the first read itself. You don't have to. It is always good to have a generic idea of the problem first than to have a deep understanding of it. So go ahead, feel free to pause the video and just have a glimpse at the problem at hand before we move on to understanding the problem. You can find a link to the problem in the description below. Alright, I hope all of you have read the problem and somewhat got an idea of what Chefina wants. Now, let's look at it more in detail. We are given a set of n ranges, L1, R1, L2, R2, all the way up to Ln, Rn. A range is basically a pair of numbers which indicates all numbers between L and R, including both L and R. For example, if we have 3, 6, this indicates the numbers 3, 4, 5, and 6. As a side note, we use square brackets to indicate inclusion of a number and round brackets to indicate exclusion of a number. For example, this particular 3, 6 indicates all numbers between 3 and 6, including 3 but excluding 6. Now, it is given that if any two ranges in the set of n ranges have a common point, they belong in the same subset. Let us look at an example to understand what this means. Consider the set of ranges 1, 3, 4, 6, 7, 8, 2, 5, and 6, 7. Let us start putting these ranges in subsets according to the definition. 1, 3 will go to subset number 1 to start with. Now, 4, 6 does not have an overlap with 1, 3. It can go to either subset number 1 or subset number 2 because the definition only states what happens if two ranges have a common point, and hence we can safely assume that we can put two ranges with no common point in either the same subset or different subsets. Next, 7, 8 has no common point with either 1, 3 or 4, 6, and hence let us put it in subset number 3. Next, 2, 5 has a common point with 1, 3 and hence will belong to subset number 1. But it also has a common point with 4, 6 and therefore 1, 3, 4, 6 and 2, 5 have to belong to the same subset. Similarly, 6, 7 has a common point with both 4, 6 and 7, 8. This implies that all the points in our particular example belong to the same subset. We have now understood how to divide the set of n ranges into subsets. Now, let us look at what Chefina wants. She wants to divide the ranges into two non-empty subsets. She can delete any number of ranges, possibly 0, to achieve this. We need to find if it is possible, and if so, the minimum number of ranges that need to be deleted to achieve it. In our previous example, we can delete either 2, 5 or 6, 7 to achieve this. This gives us one subset with 3 points and one subset with 1 point. Once you have understood the problem, it is always good to run through the sample test cases. The input format states that the first line contains a single integer denoting the number of test cases. Each test case contains a single integer n which denotes the number of ranges, and the next n lines contains two integers li and ri which denote a range. So, in our sample case, we have 3 test cases. The first test case has the range 1, 4 2, 6, and 5, 7. We can see that they all belong to the same subset, and removing 2, 6 gives us two non-empty subsets. Hence, the minimum number of ranges we need to delete is 1. In the second test case, both 1, 4 and 4, 6 belong to a single subset again, but we cannot delete any range because then we won't have two non-empty subsets. Hence, the answer is -1, which implies it is not possible. Finally, in our third test case, we have 3, 7 and 8, 9, which already belong to two non-empty subsets. Hence, the answer is 0, as we do not need to delete any range. Now that we have understood the problem thoroughly with examples, let us move on to the third commandment, searching for the simplest algorithm. In this, all we want to do is get a crude solution to the problem. That is, our main goal will be to just solve the problem without worrying about the constraints of the problem or the complexity of our solution. I had mentioned that if two ranges do not have a common point, they can belong to the same subset or different subsets. Notice that if we have two or more subsets, we can combine them in such a way that we always have two subsets because of the previous statement. So, one way to solve the problem would be to first divide our n ranges into subsets. If the number of subsets is greater than or equal to 2, we would not have to delete any range, and hence our answer would be 0. If we cannot split into multiple subsets, then we will have to try and delete the least number of ranges. To do this, we can try every possible combination of ranges and see deletion of which combination leads to two non-empty subsets. The number of possible subsets for a set is 2 to the power of the number of elements. This, obviously, will take a very long time to solve the problem. Looking at the subtasks of the problem, we can see that we are thinking in the right direction. A good rule of thumb to follow is that a CPU can run approximately 10 to the power of 7 operations per second. According to the first subtask, n is equal to 16. For every combination of ranges, we will have to check whether the remaining set after deletion can be split into two non-empty subsets. This check takes approximately n square operations. The number of combinations we have to check will actually be 2 to the power of n minus 1 and not 2 to the power of n, because we need at least two elements if we want to split into two subsets. So the total number of operations for n equals 16 will be 2 to the power of 15 into 16 squared, which is approximately 10 power 7 operations. Since we have come up with the simplest algorithm to solve the problem, we can move on to the next commandment, locating the best algorithm. Observe that when we put the ranges on the number line, you look at it in an ordered fashion. Notice that we can have two subsets in such a way that the rightmost end of one subset is less than the leftmost end of the other subset. We can visualize this by looking at a point on the number line which splits the ranges into three parts, such that one subset of ranges lie completely to the left of the point, one subset of ranges completely to the right of the point, and one subset of ranges in which the point lies. If we delete this third subset, then we are left with two subsets which do not have a common point. Our goal now is to find a point such that this third subset has the smallest size possible. Assuming that subset number 1 can have the point as its rightmost end, as shown in the example, we can consider all the possible rightmost ends for all subsets. And here is where we hit the jackpot. There are at max n unique rightmost ends for all possible subsets. These are just the right endpoints of every range. Hence, we just have to run through the right endpoint of every range, and subset number 1 will contain all ranges with rj less than or equal to ri, and subset number 2 will contain all ranges with lk greater than ri, and we have to find the minimum size of subset number 3, which has lp less than or equal to ri and rp greater than ri. The next step would be to test the correctness of our solution, and that's where the next commandment comes in. Try running the algorithm. Consider the same example. Now, we run through the right endpoints of every range. For 1, 3, 3 will be our point. 3 will split the set into 1, 3, which will be on the left, 4, 6, 6, 7, and 7, 8, which will be on the right, and we will have to remove one range, 2, 5, to get our two non-empty subsets. Similarly, we can do the same for the remaining ranges. Note that for point 8 and point 7, we do not have a valid solution because we require two non-empty subsets, and in both cases, subset 2 is empty. Thus, we can see that the minimum size of subset 3 of all the points is 1. Convince yourself that this algorithm works by running through a couple more examples. Once we have an algorithm which we think will work reasonably well, we have to write the pseudocode for it. From our algorithm, we see that for subset 1, we require rj less than or equal to ri. So, if we sort our ranges with respect to right endpoints, then when we go through every range, we will already have subset 1 available to us. From the remaining ranges, we need to find the number of ranges with LP less than or equal to RI less than RP. This can be done by moving all ranges with LK greater than RI to subset 2. Our algorithm thus becomes initialize our answer to infinity, sort the ranges in ascending order of right endpoints of ranges, traverse the sorted array, that is, for every Ri, let subset 1 be formed by all ranges with Rj less than or equal to Ri, and subset 3 will contain the rest. Check if the ranges in subset 3 has LP greater than Ri. If so, move them to subset 2. Answer will be the minimum of current answer and size of subset 3. We have to make sure that subset 2 is not empty. We can completely remove the notion of subset 1 and subset 2 from the pseudocode by rearranging a bit. Define S3 as the empty set. Inside our for loop, we need to remove all Lj, Rj such that Lj is greater than Ri. Now, the size of S1 is I, and therefore the size of S2 will be n minus size of S1 minus size of S3, which is nothing but n minus I minus size of S3. And this size should not be 0. Only then can we update the answer. Finally, we have used the current Ri as our point, and hence this range can be added to S3 for consideration. If we do not use a data structure, sorting takes O of n log n, and checking Lj greater than Ri in S3 takes O of n operations in the worst case. And since we are running through all ranges, our worst case scenario for the whole algorithm becomes O of n square. This can be used to solve subtask 2. But observe that we just have to remove all Lj greater than Ri, and hence we can have an ordering of the left endpoints in S3 in descending order. This can be achieved using a hash map or a priority queue. This way, each range can at max be removed only once, and hence the removal operation becomes an amortized O of 1, whereas addition of an element becomes O of log n. Thus, the overall complexity becomes O of n log n. Without using the correct data structure, we would have been able to solve only up to subtask 2, but with a priority queue, we will be able to solve the full problem. Try run the pseudocode with an example to convince yourself that this works. The next step now is to code the algorithm. You can find the code in C++ in the description below. As you can see, we start off by taking all the inputs: the number of test cases, the number of ranges, and the ranges themselves. We have defined our own struct called range, which holds left and right. Our vector holds all the n ranges. Since we used a custom struct, to sort the ranges, we need a comparator function, which tells the sort function how exactly it should sort. In our case, we need an ascending order of sorting based on right endpoints, and hence we have I.write less than j.write in our comparator function. Next, we define our priority queue S3, which holds only the left endpoint of ranges in our subset 3. This is to avoid writing a comparator function for our priority queue as well. Now, we run through every range in reverse order. Note that all ranges with index less than or equal to I will belong to our subset 1. While our priority queue contains left endpoints greater than our current right endpoint, we keep removing all such ranges. Now, we have to ensure that our subset S2 is not empty. Since we used zero-based indexing, the number of ranges in S1 will be I plus 1. Finally, we update our answer. Now, we also push the current range's left endpoint into S3. At the end, if our answer did not change from infinity or int_max, that means that we did not have an answer and thus should output -1. There are a few minor optimizations that can be made. Using scanf and printf instead of cin and cout can generally lead to a considerable speedup when there is large amount of input-output. We can also use the pair structure from C++ instead of defining our own custom struct. We can also avoid writing the comparator function by taking the input in reverse order. This way, sort function automatically sorts the vector of pairs according to the first element, which will contain our right endpoint. Some macros can be defined to avoid writing more code. Ultimately, these are all minor optimizations and will not affect the runtime too much. Sometimes errors creep into our code, and the best way to fix them is to test or debug the code. The best tool to use is GDB, and here I'm using the GDB debugger in VS Code. So let me run through an example, the example that we've been working on till now. As you can see, we initialize our answer to int_max first, and then we sort the array. And you can see that it gets sorted here according to right endpoints 8, 7, 6, 5, and 3. Next, we define our priority queue, and now we go into the loop. Our I is equal to 4, so we start with this particular range, 7, 8 here. And now, since we do not have any elements in S2, we just push the current range. So we push the left element of this range, which is 7, into our queue. Next, again, we see that our right endpoint 7 is that is our current right is equal to our priority queue left, which is 7. So nothing gets popped, and then because nothing got popped, the size of S2 here is empty, and therefore our answer does not get updated. So again, we push the left endpoint 6 into our priority queue. Now, when we go to the next one, which is 4, 6, we see that the right 6 is greater than 7, and the ordering is 7 and 6 in our priority queue. So again, that particular 7 gets popped, and we have 6 remaining. Again, it checks if 6 is greater than 6, which is not the case, and it moves on. Since we popped, we have one element in our S2 subset, and since we had to only pop one element, the size of our S3 will be 1, and therefore our answer gets updated to 1. Again, we push the current left, which is 4, into our priority queue, and you can see that it gets sorted. Next, we again move to the 2, 5, where the right 5 is less than 6, so our 6 gets popped from our priority queue. Again, our answer gets updated to 1 itself, and we push the next left element, which is 2. Finally, we run through our last case, 1, 3, where our right end 3 is less than 4, and so 4 gets popped again. So 2 is not greater than 3, and so we move on to the updating of our solution, which will still stay 1, and then we end the loop. So finally, we are left with answer equal to 1. This is my first time making a video, and it took a lot of time and effort to make. Hope you enjoyed it and learned something from it. A big shout out to CodeChef for giving this opportunity to show our creativity. A special thanks to Manem Library, an open source software by Grant Sanderson from the 3 Blue 1 Brown channel, and VS Code, which were used in the making of this video. Have a great day. Bye bye.